Hey guys, I'm Nick, and in this tutorial we're going to create this kind of, that golden foil, golden leaf that is actually widely used in some sort of like premium fine dining dishes. So yeah, we will be creating the reversed coating effect with these vellum leaves. We will be using vellum, we will be using Voronoi fractures, a few interesting things in the vellum solver, and so on. But for now, yeah, we are here in Houdini. So what we will have is my wedge geometry, my temp watch that I will be using for this tutorial, because the crucial thing here, and I don't know if it's a bug in 19.5 and I'm using like daily ARM build on the MacBook, but like rotating it here, this is my kind of main mesh which I use to render, and I set here the rotations 20.5, 7 and 9, but if I set them and do some stuff in the simulation, I think it just messes with that rotation and it doesn't go right. So we will be working with this temp wedge geometry, which is 0, 0, 0 at all axis and rotations. We have our grid, we have two cameras, actually I'm using this camera 4, I think, yeah, and we have HDRI and some materials in our MatNet, but we will talk about that later. So let's go into the temp watch geo node and we will go through all of these logical blocks. So first of all, as you can already tell, I really like this watch model. I think it gives a good sense of how a particular effect could be used in commercial animations. So yeah, we import our ginormous watch, we convert it to polygons, and then we do this match size thingy as we did before. Target size set to 3, 3 and 3, and scale to fit is checked. So we scale down, oh no, and delete channels, just in case you also typed something in here. Yeah, we can hover our mouse at our scene view, press H, and it should get us back to our watch. So yeah, this is our import object and resize logical block. So we actually, yeah, we imported our watch and resized it to some sort of measurable size, and then I dropped this null just to kind of, yeah, separate it logically from this block here. But here you can see that it's called to Voronoi. So yeah, we are here, we make fractures, so we scatter for 100 points. A randomized point order is unchecked. Relaxed iterations is also unchecked. I think for some sort of more organic Voronoi fracture, which consists of big chunks, smaller chunks, I mean, when we really need that irregularity, I uncheck these relaxed iterations, because if I check it, you can see that it makes the distribution just a bit easier, or just a bit like better. It tries to maintain some sort of a similar distance between points and prevent their overlap. Here, yeah, I don't think that we need that, so I uncheck the relaxed iterations. For the Voronoi fracture, yeah, we plug our scatter into the right input, we plug our null or our geometry into the left input, and here the crucial thing is to uncheck create interior surfaces, because we can check how it looks now just using exploded view. If I drop it here and plug our Voronoi output, geometry output to the exploded view, you will see how this thing looks exploded. And you can see that it is actually without any sort of interior faces, not the thing that you will do for your RBD simulation. But if you are simulating Vellum, I think that's what we actually need. So yeah, let's remove the exploded view, and now we have our Voronoi fracture done to our piece. So I think let's start with let's go and set up the Vellum. So for my Vellum, I have Vellum cloth, which is very default. Mass is set to calculate uniform. Pin to animation, I don't think that we actually need something because we don't animate it. But yeah, in the bend, the stiffness is multiplied by 0.001. And yeah, that's it for this Vellum cloth. But then I add this Vellum valid, and actually you can bypass that and your effect will still look good. But I wanted to create a bit more sort of a tension on these fractured pieces. So that's why I dropped this vellum stitch, and I make sure that my stiffness here is set to 0.01 and breaking threshold is extremely low. So type is set to stretch distance and threshold set to 0.001. So it does not make that effect complete. I mean, it's more like an additional like 5% to make it really good. And from this vellum constraints we drop two nulls, out geo and out con, and this is because we will be working in the .NET. We won't be working in the sub level. We won't drop a vellum solver, blah blah blah, and yeah, we will go to the .NET. Our vellum constraints are set. Now we need to drop something or create an attribute that will determine if that part of this golden leaf, or let's call it golden coating should actually tear away. So you can see that from our Voronoi fracture, here I have another null which is called to growth, because it goes to the growth block, growth logical algorithm, and I set two spheres. I even didn't use any sort of mountain node, but maybe you want to use some sort of mountain node. And I colorize them to be red. Here I colorize my mesh to be black. And in the attribute transfer, I keyframe this distance threshold. I'm transferring here in the attributes, you can see that I'm transferring the color data. So basically, with animating, keyframing this distance threshold from something negative to something around 1.6, you can see how this effect spreads. We're spreading that color, and every part that is red will receive the wind, will receive the velocity. So yeah, that's how we create this attribute, that color spread that will drive our simulation. And of course we will need to drop this null called outActive just for our convenience, just because we want to keep this all simple and organized, so we actually know what each block and what each node does. So now we are done with this part. We created our fracture, we created our vellum constraints, and we created our attribute that will determine if the golden coating should be tiered off from our watch. So now we have to create a few things. Let's from the beginning create collider, and collider here is our watch. Our match size goes to the null that is called 2VDB because it goes to these VDBs here. And essentially you can see that I have two VDBs, VDB for render and VDB for Vellum Collider. For the Vellum Collider, I'm using voxel size set to 0.02, VDB reshape SDF, and this one is crucial. So I have operation set to erode, and I have my offset set to 0.4. What it does, let me just merge a few things here and colorize our watch into sort of an orange and convert VDB. I want to convert this VDB reshape and I want to colorize it to be, I don't know, maybe blue. So this goes here, this goes here, and this goes here. And don't forget that in convert, we want to convert it to polygons. So here's the thing. You can see that if I am decreasing this offset, you can see how our collider is kind of protruding through the mesh, but we want our collider to stay inside. So that's why in erode, I set this offset to be 0.4. And now you can see that we don't see our collider protruding. So everything should work good in terms of collision detection, collision handling and behavior. So yeah, this is, and after our VDB reshape with that erode and the offset, I dropped the null which is called out VDB collider. For the VDB for render, I actually set the voxel size to be 0.01, VDB reshape SDF, which is set to erode and set to 0.3, and convert VDB to convert it back to polygons, because polygons is what we want to render. Cool. So now we have everything that we need. We have our Vellum constraints, attribute, VDB for Vellum collider, So we can drop our DOPNet, and in the DOPNet we will be creating all of our Vellum stuff. So once you drop a DOPNet, you will need to drop a Vellum solver. Here you can see that constraint duration set to 300, substeps surprisingly is set to 1, and I tried with substeps like 6 and 5 and 4, but actually I get some pieces of that claw stuck in my collision geometry. So yeah, substeps set to 1 actually works better for me in this scenario. We drop our Vellum object, it's all default here. For the Vellum source, we set the subpath to be outGeo and constrain subpath to outCon. It is these two that we are using here, outGeo, outCon. And then we should do some magic in the subsolver. So these pop, wind, pop, drag, and pop axis force, these all are done for kind of trying to tear off that golden coating. We will talk about them a bit later, but for now, let's check out subsolver, and this is very interesting here. So as I said in the previous tutorial, subsolver is basically a thing that allows you to dynamically import your attributes from your sub level, because if you, for example, here we don't have any temperature, our temperature, not like temperature, but our red channel color, we have its value rising here, but Vellum solver here in the DOPNet doesn't know absolutely nothing about the attributes that are changed in the sub level. So that's why we need our subsolver, and we have our attribute wrangle here in our object merge. So this object merge points to out active. So it points to this one, this null, that has all the attributes that we actually need. So that's why we can go into the DOPNet, back into the DOPNet, and in the subsolver, we have our object merge plugged into the first, this is 0, 1, 2, 3, just in case you forgot, into the first input of our attribute wrangle. And here, we just want to copy a few attributes from our out active to our DOP geometry, which is the geometry we are working on in the DOPNet. So in 19.5, I think they removed this option to just write down CDR and get the float value. So that's why to get the color, that color red, which is spreading out on the geometry, we need to create a local variable called vector CD, vector color data, because color data is vector, because RGB are 3 components of the vector, and it equals to the point function, which gets points attribute value. In this case, from the first input number 1 is here. Color data is the attribute name that we want to read, and we want to read it from the ptnum. And the concept of ptnum is that attribute wrangle goes over all points, and this ptnum means that it will get each point's color data in this function. And then we want just one channel, which is red. So we create the float red variable and assign that to be cd.r, so the red channel of the color data vector. And then mass. So with the mass, it's an interesting thing, because if mass is set to 0, nothing will happen, so no forces will be applied to that point that's mass is set to 0. But setting mass to 1 actually makes that point that constrains there explode. So for my case, I'm remapping red channel, which goes from 0 to 1. I'm remapping it using fit01 function. I'm remapping it to 0 to in range from 0 to 0.0001. The thing with this mass parameter, it's basically like in the real world, the bigger the mass, the bigger will be inertia of this particle. So if we toss something really heavy, it will have bigger inertia than something like a feather or something very, very light. So that's why in this case, we want to clamp that mass from 0 to 1, because 1 produces a bit bigger inertia that we actually want here. But anyhow, then we need to apply some velocities, and velocity is absolutely equal to the normals that we have here, and here are our normals. So yeah, that's where our velocity will be directed. So if I visualize just like, let's say 30 frames, it will look something like this. Here, while it's simulating, you can really see how only the parts that are at least some type of red, they get the mass which is not equal to 0, and then they actually react to all the forces that we apply. They react to the velocity, they react to all the wind forces that we have. So yeah, that's I don't know why I cannot preview it here. I should be able to do that here, but yeah. So here's the thing, that only these particles that that's value in color data in the red channel, that value is more than 0, they react to all the winds and drags and axis forces here. So let's talk maybe about the pop wind. In this case, the amplitude is set to 1.6, swirl size to 0.3, pulse length to 0.6, pop drags to maybe add a bit more organic feel to that pop wind. And pop axis force is used to, you can see it here, speed, you can see that orbit speed is set to 0, but suction speed is set to 6, fall of soft edge is set to 0.6, and radius and height is adjusted. So basically all these golden leaves that are on this side, on the inner edge of our watch, they are sucked into the center. So yeah. For the static object here, this is pretty crucial. So we are using our out-VDB collider that we created, and modes should be set to volume sample. Of course, collision detection should be set to use volume collisions, and division method also should be set by size. And yeah, I think all the other things are default. Here we can uncheck the display geometry. I just removed all the bounce and friction from the physical tab, just in case, so they tear off easier. And yeah, then we drop a file cache in this DOPNet. Before we drop file cache, important thing is here in the object to set it to be Vellum object 1, and not like static object, and not that shift 8, which means all objects. We just want our Vellum object 1 here. So yeah, we drop the file cache. In my case, I'm caching out 210 frames, and we can see how it goes. Yeah, so yeah, that's it. Oh, actually, I forgot one super crucial thing here. So yeah, we somehow bypassed this Vellum constraint property. And this is very, very, very interesting. So here in the Vellum constraint properties, we actually do some nice magic. So we are animating rest length scale. And if you watched my tutorial with like expanding cloth, here we are doing exact opposite. So my idea was that if that chunk gets separated from the other golden coating, like the main coating geometry, then as it flies away, I want to scale it down. But I cannot just like use p-scale or some sort of transform. I need to animate the rest length scale of that chunk. So group stretch has this rest length scale parameter. So in the Vellum constraint property, we specify that here we wanna use only the stretch group. We check that we will be using rest length scale, we will be editing it, and we wanna bind our rest scale to the distance between the current distance and the initial distance. Here you can see that I'm again getting something from the point from the first input, but you can see that we have only one input. But no, here in the inputs, I have my input number 2, which is actually input number 1. I have set it to be SOP, and I go here in the SOP pass, I actually set it to be out active, that same out active that has not only parameters that we need for our growth, but it also has all the geometry and all the points. So that's why we can go back onto our DOP network, and we can calculate the distance between where the point position now and the result of this function called point. And we grab the position from our out active, our first input, each point, and we basically, with the distance, we calculate the distance between 2 point position that is this frame right now and our initial position. And because I don't want any artifacting of the Vellum, I set that if expression. So if the rest scale, and rest scale is rest length scale here. So rest scale is more than 0, 1, I am subtracting the distance from the initial rest scale, which is 1. If the rest scale is less than 0.1, I just set the rest scale to be 0.1 because going smaller than 0.1 might actually produce some artifacts and the Vellum simulation will be super slow and blah blah blah. So yeah, the main idea here is the further this chunk of this golden foil travels away from the watch, the lower the rest scale and the smaller that chunk actually is. This is how you can scale different Vellum sims. So now we need this distance again. So after our file cache, after that thing that we cached everything and we have our animation done, I want to calculate the distance once again. So in this attribute wrangle, I just drop to the 0 input, I drop my file cache, and into the first input I drop the time shift, which is bind to the file cache, but it's frozen at the frame 1. So if I go here and select this time shift, you can see I can drag how long I want, but in the attribute wrangle here, I calculate that distance again that we will later use for our shader. Then I drop the Vellum post process, which is bypass for now, but yeah, just take the extrude by thickness and subdivide it one time is absolutely enough. Then we drop the material to this coat layer, which is called coat material. And here you can see I have my VDB, which also gets material, which is called base material. And just to visualize it, I colorize it. So, oh no, actually for this coating material, this color actually means a lot. So this color node has color type rem from attribute, and attribute is set to pt dist. So the range is from 0 to 0.5. And you can see how here, for example, and I assume we still will need to get that Vellum post process. But the main thing is here you can see how the chunks that are further away from our initial geometry are colored in black, and they are getting darker and darker, and our chunks that stay or have some sort of base position or haven't got far away, they are all white. For this one, I just colorized it into sort of blue just to see if I don't have any protrusions, but nope, everything is good, everything is cool. And yeah, now it's time to reverse it. So we drop a retime node, and the evaluation mode is set to fit range, and output range is 210 to 1, and input frame range is 1 to 210. Then the only thing I added is normals and out. So let me bypass the Vellum post process, and I can show you how this all looks together. So yeah, I will enable Vellum post process and just go to the frame sort of 139. I think it will be good to show you both materials, and we can talk about redshift, about our cameras, about our lights, and etc. So here I will just add new paint tab type, redshift render view, set the camera to be camera 4, and fire up my render. And actually now we can apply the transforms. So it's 20.5, 7, and 9, 20.5, 7, 9. And let's zoom out. So yeah, now we have all of our materials here, I think. Yeah, that's cool. I want to talk about a few materials here. So before we actually start talking about materials, you can see that I have my grid here, right? So here's my grid. I can show you it by going to my visibility settings in the Redshift OBJ, and you can see that primary ray visibility and visible in refractions were unchecked. So if you want to render out without background, you can uncheck this primary ray visibility, but then because these chunks here have lower opacity, because our opacity is actually bind to our PT dist. So these chunks have lower opacity, and because we have this grid visible in refractions, we are seeing that grid through the low opacity of these chunks. So if I uncheck visible in refractions, this looks much more like just a regular low opacity thing here, rather than just like a glowing something, right? So this is crucial if you want to render it out without the background. So for my watch, we can actually select just small part here, and maybe let's render this part out. And while it's rendering, we can talk about the materials which we have here. We have grid material, coat material, and base material. So for my, and don't judge this resolution here because it's more than it should be actually. So in the coating material, for the base material, this is set to the preset set to plastic, and I'm using two noises, one for the bump map that you can see here, and one for the roughness map, and this is FBM noise, which I discovered lately, and it's really good for sort of imperfections in the roughness map. So yeah, octave set to 10, and this goes into my roughness channel. I probably can visualize it if I go into and plug it into the diffuse color and refresh the render. Yeah, you can see all these subtle thingies here. So this, because it's very bright, it's more about like a rough material, not that glossy. But yeah, let's reconnect that into our reflection roughness channel. And this one is just a turbulent noise, super small noise that we plug into the bump map. Height scale set to 0.001. If I remove it, yeah, you will better see the roughness map, which I really like here. But yeah, let's get it back to the bump input and see that kind of like a soft touch plastic thingy. And for our coating material, which is very interesting to see here, we again use Maxon noise, this same FBM. The only thing, this noise is a bit darker because I wanted a bit more glossiness in this metal here, but basically the preset is set to copper. I think I modified the reflectivity and metal edge tint just a bit. And then here we have our particle attribute lookup, which is CD, which is our color data is bind to our PT dist. So everything that goes away from our initial shape here is black, so will be transparent. For the grid material, it's actually just a gray rough grid, so nothing fancy there. There's also one thing in the redshift settings. Here you can see that I am enabled motion blur and started set to 0.05 and set to 0.95. So pretty big values for motion blur, but I think it sells this effect really good because without motion blur, let me show you. Yeah, it's just too rough, and with motion blur, yeah, it has that nice blur on the edges. To get that motion blur, don't forget that here in the Redshift OBJ settings, you should check Mesh Deformations Blur from Velocity attribute and enable all these, basically all these things for motion blur should be enabled. So yeah, for the RS slide dome, I'm using my favorite brown photo studio, the saturation set to 0, rotated. Oh, actually, I even didn't rotate it anyhow. But yeah, I think this effect is pretty decent. I'm really satisfied how it turned out. And that's it for this tutorial, guys. If you have any questions, please feel absolutely free to reach out to me in Discord, in our Cozy Play server, or on Patreon. I will be glad to help you out with any questions you have. And I really hope that you learned a few cool tricks today. And I'll see you guys next week. Bye!